Okay, the topic of climate change. Let's dig in. Here are some goals. Again, the goal, or rather, I say that every time. Is the goal and the objectives for this lecture. As usual, you can use these to make sure that you're understanding the content. And then here's just a little reference to stuff you should already have checked out or that you should know about that will help deepen your understanding of this topic. And the topic is climate change. So again, we've talked about climate. You should understand the multiple factors influencing climate or the long-term pattern of weather changes in region. And the current reason that those weather patterns are changing and the best evidence that we have about why. Okay, so the style of this lecture, again, keeping in mind a lot of these I use in my in-class sessions. And so I've tried to adapt them so that when you're online, you can at least try to, you can simulate the same kind of engagement. So for yourself, think about what are those factors shaping climate on the Earth. And I showed you a different graph that is a similar concept to what we're looking at here. The difference, of course, here being that you are seeing only a 200-year time scale, less than 200-year time scale, as opposed to in the graph that I showed you before, if you want to go back and look at it from the climate slides, was looking at a much longer time scale. But these factors we have these greenhouse gases, right, which trap heat and cause a net warming pattern. And since the beginning of the Industrial Revolution, we have slowly been putting more of those into the atmosphere. And then right around the Great Acceleration, we start to see this exponential growth in those climate drivers. We also have slight variation in sun's energy output, right? It is a burning star, or I guess that's redundant, but it is a star or a burning ball of gases in the sky. And so there are going to be variations in the energy coming out of that. And then we have this green one is our land use changes, which have had, again, are going to be having a warming effect. But then there's some counteracting of effects if you're just looking at albedo. And then finally here we have these aerosols, right? And so I mentioned volcanoes and other sources of aerosols can have this cooling impact on the planet. And then we have, of course, the pollution aerosols as well. So there's climate change, which is just general changes in climate patterns on the surface of the Earth that we've been able to detect over hundreds of thousands of years. And then there is anthropogenic climate change, which is human-caused climate change. So that's what this question is asking about. Why do scientists believe that current climate change patterns are anthropogenic in nature? And the reason is actually not that complicated. Someone once said, one of my colleagues once said that it's kind of astounding that the public will trust much more complicated science, for example, trying to predict weather patterns on any given day. But these longer term climate science, there's more resistance to. And that probably has to do with not liking the message very much, which I can't say I blame the public. I don't like the message either. It's not terribly uplifting. Okay, so backing up, why is this anthropogenic? It's just a simple disruption of the carbon cycle. If this carbon cycle has this has the fast carbon cycle, which is kind of this neutralizing process, you have your consumers, producers bringing in carbon dioxide, consumers putting out carbon dioxide, decomposers maybe putting a little methane into the atmosphere, but providing nutrients to the producers. And so this is this kind of carbon neutral, if you will, process. And then you have this long-term carbon being drawn down into deep earth deposits, some of them ending up in sediment, some of them moving into volcanoes, and some carbon dioxide going back into the atmosphere through these volcanoes. So what have humans done differently? Again, we are now emitting 30 billion tons of carbon dioxide into the atmosphere. So this is a huge disruption of the cycle. Where is this carbon dioxide coming from? And in that, I'm going to mention there are other greenhouse gases as well that are going into the atmosphere. So we focus a lot on the carbon dioxide, but there's other greenhouse gases, particularly methane is another major source. So where are they coming from? Right here, nice little caricature for you. We have cars that are burning a carbon-based fuel, right? Either diesel or gas. Those are the major fuels that we use right now, and those are carbon-based. Even if you were burning biodiesel, that would be carbon-based. And again, that's just a carbon-based molecule interacting with oxygen in the atmosphere. It burns, it gives off carbon dioxide, water, and vapor, and some other pollutants, right? So we're getting carbon dioxide out of that. We are, our factories are using electricity. Most of our electricity production produces carbon dioxide as a byproduct. They are also directly processing chemicals and often having their own combustion reactions that are going to be putting carbon dioxide. Anytime I say combustion reaction, just understand burning puts carbon dioxide into the atmosphere. Then that's, so we're getting that. And then landfills have decomposition, and that decomposing, those decomposing materials in landfills are actually producing methane. And that methane, if it's not burned, now most landfills will responsibly flare, so they'll just light the methane on fire and it'll reduce it to carbon dioxide. Because as you know, methane is a stronger greenhouse gas than carbon dioxide, so it's better to burn it and reduce it to carbon dioxide than just let it go directly into the atmosphere. So that's a source. Methane from cows. Oh, and I have all these fun labels. I forgot about them. So methane from cows and also carbon dioxide from agriculture and fossil fuel use. We're getting some nitrous oxide in there as well, which you learned about in the nitrogen cycle. And then with deforestation, we're not actually, I mean, when you burn the trees, yes, you will put carbon dioxide in the atmosphere, but you're also removing a carbon sink. So these trees would be pulling carbon dioxide out of the atmosphere, and they're no longer doing that. And then also to mention, I mentioned carbon dioxide with your factories, but you also, CFCs is a huge thing with factories. And again, your nitrous oxide. So the carbon, where this is just a similar concept here, where the carbon dioxide is coming from and where carbon dioxide could go. So most of it is sitting in our atmosphere. Some of it is going to get sequestered back into the land. And then we're actually putting a whole lot of it into the oceans. And this is causing an additional problem of ocean acidification. And we'll get to that in a different lecture. And this is just looking at the essentially another view of the Great Acceleration, right? So right around here, we're getting to the last 50 years. Well, I keep thinking it's 50, but really 70 years now, and we're on this exponential growth curve. Again, remembering this is, you have year on the x-axis and then a primary and a secondary y-axis. This one looking at carbon dioxide and nitrous oxide, and over here we're looking at methane. And just because those are on completely different scales, and so that's why they're graphed that way. So you can see a similar trend on different scales. I'd like to ask this question. What country emits the most CO2? Think about it. What comes to mind for you? And the reason I like to ask this question is because so this is actually a clickable slide. You can click on this one and it's going to take you to a website and you can play around with this. If you look at root numbers or gross numbers, absolute numbers of carbon dioxide going into the atmosphere, what you will see is, yes, in fact, people kind of have this stereotyped idea that China's at the top of that list. And China is very high up on the list. However, if you look at it per person, so if you think about, again, carbon dioxide is being produced to contribute to human well-being. We've already looked at how it's tied to GDP, you know, fossil fuels are tied to GDP, and that's tied to all these indicators of how kind of a good way of living that we've come to expect and want. And so if you think about carbon dioxide as sort of being allotted per person in terms of that idea of an ecological footprint, the US is actually pretty high on that list, and much higher than a lot of the nations that you would traditionally think of as sort of, seems to me that there's a little bit of a campaign going on in some of the media. And so again, noting here that, you know, United States is pretty high on the list. And then interestingly enough, some other nations that you wouldn't expect end up, well, that you wouldn't expect to be quite so high. And part of the reason that this happens is also you have to keep in mind exports, right? So what are these nations producing, and who is consuming those things, right? So all of this goes to say, I encourage you to click on the website and you can really kind of play around with the different figures and see how we measure up in the United States. Okay, so what is the Keeling curve and what does it tell us about anthropogenic climate change? Okay, so if you look at the Keeling curve, right, this is, and hopefully you spent some time on that website. If you haven't yet, I hope you do that. And what you can do is look at this movement of carbon dioxide in the atmosphere, or I guess that's not, movement isn't the right word, the varying levels of carbon dioxide in the atmosphere throughout the last, again, 50 to 60 years. And so on Mauna Loa, which is a volcano in Hawaii, there is an observatory that has been monitoring carbon dioxide in the atmosphere now since the 1950s. And that the curve of the path of carbon dioxide, or that concentration, has been called the Keeling curve. And hopefully now, I'm not going to repeat it because I want to make you look it up on your own if you don't remember, you know why it is oscillating up and down throughout the year. Okay, this is another clickable slide. It's great and yet slightly harrowing because you can look at it'll take you in real time, looking at the variation in carbon dioxide throughout time, again, as captured from these observatories, right? So we have these observatories now all over the globe that are measuring carbon dioxide in the atmosphere. And what you can see is that with the same trajectory that we've been looking at since the Great Acceleration, we're seeing of carbon dioxide in the atmosphere. Okay, so what about those Milankovitch cycles? Remember, I warned you in the last one. In this, you can see thousands of years, hundreds of thousands of years. So this time scale, we would expect to be seeing Milankovitch cycling, and that's these ice age cycles that we're seeing here. However, what are we seeing here, right? Right here is this spike that we don't have recorded. And this, now that doesn't mean, of course, you know, there could be some variation in there, but it's looking unprecedented. And this has all been looking at the Industrial Revolution, right? So 1800 to 2000, we see this spike, this exponential growth in carbon dioxide. And as you know, we are now way up here. And if you look at the long time scale that we have this record for, this is a pretty good indication that this current spike is human induced. And again, knowing just our basic chemistry of what happens when you burn all of these fuels, that carbon dioxide has to go somewhere. And then the added aspect that those fossil fuels are buried deep in the earth, and we're digging them up, right? And so they've been in there for millions of years. We dig them up, we put them in our atmosphere. It is pretty easy to understand that it's going to that there's going to be some sort of consequence to that. And then I just like to throw this one in here for you to think about this idea of radiative forcing, right? So what is, how are the different things, right? Because there are, again, the Earth is a complex system. There are things pushing the climate in one direction or the other. There is natural non-anthropogenic fluctuation in carbon dioxide and other gases, right? But what you can see, of course, is this increase in anthropogenic forcing that is thought to be driven by these humans releasing greenhouse gases into the atmosphere. And then again, just keep in mind this idea that some greenhouse gases are considered, quote, better or worse. And that goes back to that idea of some greenhouse gases have a stronger forcing potential. So a little goes a long way, and maybe not in a good concept of that statement. So have we started to see changes in the temperature? This is interesting because I feel like even since I've been teaching this topic now for a minute, as they say in the South, it's been a minute. It's been almost 20 years that I've been teaching climate change. And what's interesting to me is how I feel like I would have to show charts before to talk about this change in temperature. And most people can see it now. Yeah, it's becoming more and more obvious to us. The record-breaking heat days every single year. You have to kind of willingly try not to see it at this point, which makes my job a little bit easier. But if you want to chart it out with some good temperature anomaly data, which you, as I said, get a chance to play with this data in our class. It is publicly available data, at least for now. And you can look at these temperature anomalies throughout time and what is happening. And of course, this is the recent record, right? Which is good because that means that we're working with even more reliable data. What we see is this trend, right? We're moving in a positive, so the annual versus 5-year average. And again, you're going to get up and down patterns. You're going to have warmer and colder years. That is just natural fluctuation. But you have to look at the trend, and the trend we see is this increasing warmer time periods. And again, this fits our concept and our understanding of the impact of greenhouse gases on atmospheric temperature. Okay, so where are we going? Note there's a topic on, there's more climate change to come, and looking at climate modeling, we'll spend a little bit more time with this. But it's not great. So the predictions are, so we expect to continue to see warming. We don't know exactly how much warming, and that's the difference between these. What modelers do is they run different scenarios. So they take the parameters, they take the things that we do understand, they construct a computer model out of it to come up with different predictions. And most modelers, what they'll do is they'll come up with like a best case scenario and a worst case scenario. And that's what the best climate scientists in the world have done in this report called the Intergovernmental Panel on Climate Change, or the IPCC. They put out a couple reports. One of them we look at in a bit of detail. And so the worst case scenario is being on this trajectory to warm potentially 4 degrees Celsius by 2100. And best case scenario being closer to 1 degree Celsius. Now, you might recall, if you paid any attention to the news in the last few years, although there's been a lot to pay attention to, you might recall that there was a report that came out a couple years, about 2 years ago, maybe, that said that things were much worse than we expected. And that, in fact, we tend to be more on this trajectory. And the recent report is trying to get us to stick to 1.5 degrees Celsius as a best case scenario. We'll talk a little bit more about that in some of our chat sessions. But yeah, what it comes down to is we seem to be more towards the worst case scenario than the best case scenario. Again, knowing that these climate models are now 10 years old. Okay, so we're going to expect change in average surface temperature, and note it's not going to be distributed evenly across the globe. We always see heat moving towards the poles, and it's one of the reasons why we're seeing, if you've again tracked any of the news, these record-breaking temperatures that are happening at our poles, and that where our ice sheets are actually melting much faster than scientists had originally hoped. And that's because of some of these feedback loops that happen with the warmer temperatures, creating warmer microclimates, and then the rushing water causes more quick melting. And so we're actually on track of some of the more dire models that we've come up with. What are some other global impacts associated with climate change? Okay, so we get it. The temperatures are going to get warmer. We are relatively hairless animals, and if you're like me, you like the heat. So why should I care? Right? There was a comic who had a funny joke about that. Well, actually, one of the biggest reasons you should care is the water cycle. So the water cycle and our precipitation patterns are driven by atmospheric temperature. And so one of the reasons why we're starting to see this in very tangible ways, but I think it's difficult for people to connect to climate because there's a few leaps in understanding there. But this increased intensity of storms and actually increased drought patterns. And the reason this sort of craziness of precipitation happens is because you have these warmer temperatures in the ocean that are causing increased storms, right? So we just know from years and years and years of data, warmer oceans cause worse hurricanes. It's one of the reasons why we're on track for yet another terrible hurricane season. And so there's one factor. Another factor being increased temperatures cause increased evaporation. And we are, quote, the watery planet. So we're evaporating more water into the atmosphere. Our atmosphere can actually hold more water because it's hotter. And then what happens is water has an 8-day residence time in the atmosphere. It has to fall. So when it rains, it pours. And it's one of the reasons why it seems to me on my time, my short time scale, that those long days of drizzle, we see a lot less, and instead we get these dramatic storms coming through, and then it's dry and hot, and then a dramatic storm, and again that has to do with that the amount of water that's ending up in the atmosphere, and then how quickly it has to fall, kind of all at once. So just unpredictable precipitation patterns. So these floods that we've had recently as well, a bunch of people had huge damages happening to their land for the first time ever in their families' multi-generational farms. And this is all related to these changing precipitation patterns that are becoming less and less predictable and more severe. Sea ice extent. So we're having melting sea ice. Quick side note here, students often want to talk about melting sea ice as being what causes our sea level rise, but sea level rise is actually mostly caused by our thermal expansion of water. So I think you all probably learned at some point that when things are hot, they expand. I remember my science teacher would do some cool trick by like heating up loops, and you could make things fit. Anyway, when things are hot, they expand, and things when they're cool, they shrink. And so our ocean, as it's heating, is expanding, and that is the biggest cause of our sea level rise. And then some melting land ice could have an impact as well, but the sea ice is floating in the ocean, and when it melts, it's not actually, it decreases in volume. But that was a side note to this. Melting sea ice is certainly a problem for the reason that we showed about the thermohaline circulation. That would be a big problem. There's also habitat, and then there's also the effect of decreased albedo at these polar regions. So as we decrease the albedo of these regions, we expect the Earth to warm even more. We'll get to this. This is ocean acidification, but one of the things that we're seeing is with this increased carbon dioxide in the atmosphere, we're ending up with more acidic oceans, and we'll talk about why in a different lecture. And then again here, this sea level rise. So we have different scenarios of where our sea level will end up. which given that most of our settlements are on coasts, this is a potential problem. So which scenario is correct? We run these models, and we're going to dive into this again a little bit more with the models, but we run all these models, and which one's correct? Well, we don't know. We certainly have, however, what we can do is we can run a model, and then we can track which one we seem on the path of. So again, all of these are different models, and then here's some historical data. And so, you know, as we move into the future, which track we stay on is going to depend in part on, you know, our understanding of the science, but also what we do about it. Obviously, we have a bunch of different options. Unfortunately, for me, it's slightly frustrating because I remember learning about this in elementary school way back here before, ironically, there was less resistance. Things got quite political in here, and discussions about, you know, what are we gonna, maybe we'll do something about it. And of course, 40 years later, here we're sitting. And so a lot is going to depend on what we decide to do about this. We have steps to go. We have some not terribly painful steps to go in the right direction, but we don't always go in that direction for reasons of multiple reasons. Okay, so climate change. That's most of the science there, and you'll get to play around with some of that data.